A lot of people are not even aware about IgG4. And if you've never heard about it, you should want to learn what this is about and why it's very, very important. And by the end of this presentation, which will not be too long, this is something you should be able to then speak with family members about and explain to them why we should ask more questions. One of the important premises that I've learned through the pandemic is that you don't necessarily focus on what you're being told to focus on, but you look carefully at what people are choosing not to make any reference to. A really, really important difference. And IgG4 is one of those points. So let's just get through a few basic things. The first thing you have to realize is that this is a pattern that we haven't really seen before with any vaccine. The only time we see IgG4 is usually when we're trying desensitization to allergies. So this is quite unusual. And so when it first came out, what we were seeing was a class switch towards non inflammatory, spike specific IgG4 antibodies after repeated SARS-CoV-2 mRNA vaccination. And it's very important to note that this is not specifically all about COVID vaccines. This is specific, quite specific to mRNA vaccines and their characteristics. So it's a very unusual pattern that we hadn't really seen before. So let's just get a few basics of the science. The first thing is, as usual, you have the spike protein. The virus is this big gray globule, and on the surface, you have multiple spike proteins. Each one of them is a trimeric formation, so each one has a receptor binding domain that can then bind to the receptor and get in the cell. There are about 25 of these on the surface, so this is a bit more than it would look like. And this is a closer up look of to what the spike protein would look like. This is the bit that would be embedded in the membrane of the virus. And on the top here is where ACE2 or some of the other entry receptors would bind. And so this is what we then used, and I say we with a big we, was then used to then trigger the immune system to be able to target the virus. And this is why we had mRNA vaccines that were produced. And in order to understand how the immune system works, there are just some basic premises, principles, is that they produce antibodies, IgG antibodies, usually the longer lasting antibodies. You usually have IgM, IgA, IgG. And when we're talking about antibodies, very often we're focused on the IgG antibodies. And you have on this side IgG1 and IgG3, which are inflammatory antibodies. And then you have over here IgG4, which is more like the tolerant antibody. You'll understand what that means in just a moment. And this is just the image of the virus again, with it targeting. In the case of the vaccinated cohort, it would be primarily targeting the spike protein. And that's a different conversation as to why that's relevant. But let's break down the immunoglobulins because this is a very important part of your immunity. And your immune system, specifically plasma cells, will produce antibodies, which are like missiles to target specific characteristics on viruses, bacteria, fungi. It targets many things. And so when you look at your immunoglobulins, this is not an image depiction of it. This is just IgM. This one is usually pentameric, so it's five of them connected together, so it's quite big. IgGD, we're not quite sure what this does, so we don't focus too much on it. IgGG is a long-term antibody. IgA, if it's secretory, it's in the mucous lining and can be in the bloodstream as well. And IgE, which is more the allergic kind of antibody. But out of all of these here, the primary one is IgG. And this is then broken into a number of subsections. IgG1 IgG2, IgG3, and IgG4. And to simplify it, forget about IgG2 for the time being. We'll not talk too much about it. But IgG1 and IgG3 are the primary antibodies that trigger inflammation and cause your immune system to react. Conversely, because of how the body works, it always has a balance, and the balance is IgG4. And we oftentimes describe it as the immune tolerant antibody. And you'll understand why it's important in a second, because your immune system can overreact. And so the typical or the classic example of IgG4 is with, say, a beekeeper. He's dealing with bees. Even though he has covering, he can get stung quite often. You don't want him to have very severe responses to the bee stings. And so in this case, the immune system will recognize, okay, he's being stung all the time. We don't want to overreact to it. And so therefore, the immune system will then suppress the immune response with IgG4. And that's a basic premise because, as I said, in the context of everything is about balance in terms of immunity and health. You don't want too little, you don't want too much. You're trying to get everything just about right. And so IgG4 has an important place in balancing some aspects of the immune system. It's just that who thought it would be related to vaccines, where we want to stimulate the immune system against a future pathogen? Anyway, so here is the principle that is now my thought, is that a significant proportion of the IgGs are produced, IgG4, and what they would then do is bind to the virus. And when you have this, so if the virus then gets in the bloodstream and you have IgG4 bound to it, it's telling the immune system to back off. You don't need to worry too much about this. This is not a problem. You can relax. We don't want you to overreact to this. And this then causes the immune system to back down. It could be, in my explanation, one of the main reasons why we are having high circulation of virus in highly vaccinated regions. Some people would argue against that, but to me, that makes perfect sense. Additionally, I would go as far as saying that I think it's one of the major reasons why we could see reduced severe COVID-19 in vaccinated cohorts as well, simply because of this immune tolerating effect. And when we talk about the immune tolerating effect, what numbers are we referring to? And when we look at this paper here, and it was the same paper I'd shown at the start, you have an almost 4,000% increase of IgG4 after mRNA vaccination. And it's showing you here the different ones: IgG1, IgG2, 3, 4. They showed it after the second dose, after the third dose, second dose, third dose, and again, second dose, third dose, second dose, third dose. And you can see the IgG1 stayed stable, a little increase. IgG2 went up a little bit. IgG3 went down a bit by the third dose. But when you look at what happened to IgG4, it was a 38 times increase after people were vaccinated. And when this first came out, this was huge. It was like, wow, how can this be explained? And very sadly, I think the scientific community just kind of ignored it. They said, well, maybe it's not so significant. You have to prove that it's significant, that kind of rubbish. And the question was, is if we haven't seen this before, you've got to take this into consideration as to the relevance. Why does it happen? Does it have an impact? Is it relevant that the impact occurs? All these questions just seemingly got ignored. And so when you look at what happens here, and this is another paper here looking at the class switch towards spike-specific IgG4 antibodies after SARS-CoV-2 vaccination. In this case, they were looking on what happened with infection history. And so the first thing you have to look at is actually this slide here. And when you're looking at the colors, blue means IgG1, orange means IgG2, gray means IgG3, and yellow means IgG4. Okay? This is what happens after someone just got COVID and they're convalescing. And you can see that the majority of their antibodies are blue, which is IgG1, which is what you would expect, 90%. There's a tiny fraction, 1%, that's IgG4, some IgG3, and a tiny amount that's IgG2. This is natural immunity. And as I said, because I trust the immune system, and this is just my perspective, I think that anything that has been God given is likely to be of superior standard than anything we can do. That's just my paradigm. It may not be the same for other people. I always look at what happens in natural immunity to try and judge the relevance of what happens beyond. And so when I use this as a baseline, then we look at the situation where someone was already infected and then had mRNA vaccination. And in that case, it drops to about 88% from 90. That's still not bad, but you can see immediately 9.3% of the antibodies are IgG4. So there's a very clear shift straight away, even in somebody who has been convalescent and then vaccinated. And again, I make the point, as I said, because I trust natural immunity, if somebody had natural immunity, I still don't understand. Maybe I'm slow. I just don't understand why they would need to be vaccinated. We don't do this really for any other disease. Maybe COVID is special. That's why it was done. I don't know. As you can see, hopefully you pick up my sarcasm. Anyway, going back to the information here, when somebody had mRNA and then got an infection, only 50% of the antibodies are IgG1. 41% are IgG4 tolerant. Tiny amount are IgG3, a little bit more are IgG2. So that's very important. So meaning that if somebody had the mRNA vaccination, and that's a significant proportion of the population, then they got an infection, your anticipation would be that almost 50% or 40% of their antibody count would be tolerant antibodies. That's very significant. When you compare it, as I said, when you think of the convalescent where 90% are IgG1, in this case, only 50% are IgG1. So their immune system is shifted towards tolerance. When you then look at mRNA with no infection, or then you see 50% again IgG1, 45% here is IgG4. Now, they did compare it to the vector vaccines, and they still had an IgG4 impact, which is 16.6% compared to 45%. And so part of the reason is the spike protein, because in both cases they're using the spike protein. But the mRNA tends to have a much stronger push towards IgG4. The question should have been from the scientific community, well, why? Why would this occur? And that's fundamentally because the spike protein, as indicated by how the immune system responds to it, the immune system tries to avoid the spike protein. It's a really interesting thing when you look at what the immune response is after natural infection to COVID. Only 20% of the epitopes are targeting the spike protein. Very often, a large proportion of the epitopes are targeting other parts of the virus, not the spike protein. And additionally, if you weren't aware, you can't get long-lived immunity to the spike protein. The immune system literally refuses to remember it, potentially because of the reactions that can occur. So from every angle, it seems that the immune system is having issues managing the spike protein. So the question you may ask is, well, what's the relevance of this? Well, here is where I think it becomes complicated. You have at the moment where people are not responding adequately to infection and they are getting viral dissemination throughout the body. And the virus is then infecting the endothelial lining, the kidneys, the gut, the brain. And because the immune system is in tolerant mode, it is not actually dealing with the infection. So, my question is, if the immune system, because of the production of IgG4, was blocking or reducing a cytokine storm, what happens when the IgG4 levels fall? When they go down, do you have a rebound response where you have a worse cytokine storm? Now, what a lot of people don't realize is that we recognize the cytokine storm in the first part of the pandemic because it affected the lungs. And if you can't breathe, everybody notices. And so when you have a lung cytokine storm, it's very obvious. But what happens if it's a kidney cytokine storm, a heart cytokine storm, a brain cytokine storm, an intestinal cytokine storm? Suddenly it gets very difficult to pick up. It's not so easy to work out. And this is part of the reason why I'm concerned is that if we are not careful, if we don't understand this point about a rebound hyperimmune response involving other organs, a lot of people will be sick. We don't know what's going on, and we don't recognize that it could be an ongoing cytokine storm just affecting a different organ in the body. That's where medicine gets really complicated. And the reality is that if we don't figure out ways to address this, or if we don't actually focus on this properly, we will not be able to find ways to mitigate it. So, for those people who are interested in understanding more, make sure you look up this course, Spike Detox. Does everyone need one? It's very important because coming up shortly, I am working to find a way to get tests out there so that people will understand whether or not they are at risk. Because if we have ongoing spike circulation, and we start having hyperimmune responses to it, that could be a very significant clinical piece of information. We have a lot of work to do, but what you mustn't do is allow anybody to distract you from very important questions. If you ask the question to anyone in the scientific community, first check if they're even aware of IgG4. If they're not aware, give them some education and tell them to go and look it up. If they are aware and they discount it, that's a red flag because it hasn't properly been investigated and no one is really sure what the longer term impact is. Some people use that to say, well, if there is no evidence of a problem, we shouldn't worry. No, because you haven't looked. That's why there's no evidence. And so, therefore, there is a responsibility to keep poking this bear. Don't let it disappear. And that's why I mentioned it again. We've been talking about this for a few years now. Doesn't seem it has shifted. And I suspect when we're coming to understanding the cytokine storm, the spike induced autoimmune response mechanism that I've been talking about, we need to know how it occurs and what we need to do for the future. Have a great evening.